Hi, everyone, and welcome to the faculty roundtable session for the USC Viterbi School of Engineering. This is another one of our faculty roundtable sessions from the Ming Hsieh Department of Electrical and Computer Engineering. My name is Paul Ledesma. I'm the Executive Director of Undergraduate Admission, but you're not going to hear a lot from me today. I'm just here to facilitate the discussion, and let's get directly to the stars of the show. I want each of our faculty members who are joining us today to introduce themselves and tell you a little bit about their background. And then after they do that, I'll tell you how today's session is going to run. So, Dr. Mitra, would you like to kick it off?
Sure. Hello, everyone. I'm so glad that you're here with us. My name is Urbashi Mitra. I'm a professor in ECE, as Paul indicated. I've been here for about 23 years. I do a lot of work in what we call now model-based machine learning with a variety of applications, including wireless communications, microbial communities, cognitive radio, and also lately chemical engineering. So a wide variety of topics.
Fantastic. Thank you. Dr. Khan.
Hi, everyone. I'm a new faculty here. I have been here for 1.5 years. My work is in flexible electronics, printed electronics. We print electronic devices, and we also look into hardware-enabled AI to make wearables, implantables, ingestibles, all sorts of medical devices for precision health and psychiatry applications.
Fantastic. And as our newest faculty member, what we're going to do is have you answer every single question first, and then we're going to allow our other faculty members to see whether you got it right or not. So get ready for all of that. Professor Gupta, Dr. Gupta.
Hey, I'm Sandeep Gupta. I've been here a long time, 32 years. My work, my research is in the area of design of new types of circuits and systems using the existing technology and also newer type of devices that are emerging, mostly focus on computational circuits that do computation. I'm also the director of our honors program school-wide. That is an undergraduate program, so that may be relevant to this group of attendees.
Fantastic. Thank you so much for your introductions. And for all of our guests out there, again, thank you for joining us. We're going to run this up until 4 o'clock, so we have the hour to get through that. That means that we're going to talk about a lot of things, but we might not cover every possible thing in the world, but we'll do our best to cover everything. As a reminder, today's session is all about electrical and computer engineering at the USC Viterbi School of Engineering. It will not be on admission, and we will not be discussing admission. We have plenty of admission information session on our website. Lisa's in the background. She'll put a link in the chat for you so that you can register for our events page. If you ever want to register for an admission session, join us for virtual or in-person sessions that are coming up. We have a lot of them, but today is all about the academics. It's about the curriculum, it's about the major, it's about the classes, and about the research, and that's what we're going to be talking about today. The first half of the program, I'm going to be leading the discussion with a bunch of particular questions that will help you understand more about our program related to electrical computer engineering. Then when we get to that, then I'm going to open up the Q&A feature. So right now, everything's been disabled. I just like you to listen and absorb everything, but think about questions you want to ask. I'll give you a high sign a little bit later in their session here today where you can open up and ask questions into that, and we'll open up that Q&A button at the bottom of your screen. When you see the Q&A button come up, that's when you can add a question in, and then it's going to be up to you as an audience to decide which ones we answer. You can add as many questions as you like, and then you can upvote questions. And it's a democratic process. We will answer the most popular questions first until we hit that hour line. So that's what we're going to do. I hope you're ready to join us, and we hope we're having a good time to talk about electrical and computer engineering. So without further ado, our first question, probably a very simple question. Whoever wants to take it first. It's a simple question, but it's probably complicated in its answer. What the heck is electrical and computer engineering? Can you help us understand what this discipline is, especially because it's got electrical, it's got computer, and I'm a high school student, and I don't really necessarily know exactly what I want to do. Ubli, do you want to kick us off with this one?
I somehow knew you were going to ask me. So the beauty of this collection of faculty is that we all work in very distinctly different parts of electrical engineering. So I suspect we are each going to give you a taste of what happens in our slice, if you will. And so the areas that are relevant, or sub-areas, if you will, that are relevant to my particular expertise include what we call signal processing, communications, a little bit of controls. A lot of what we do is manipulate signals. So colleagues, for example, in signal processing might design pattern recognition mechanisms or voice recognition mechanisms. You may have heard of natural language processing. That's something that happens in our signal and image processing group. We also have colleagues that create improved magnetic resonance imaging strategies, both helping to design waveforms as well as decode them. I mentioned that I work in wireless communications, so we come up with mathematical models for how radio signals are transmitted, how they're distorted, and come up with clever strategies to either shape those signals or also undo distortion, et cetera. Robotics is another part of electrical and computer engineering that resides within our controls group. Perhaps surprising to some of you, but a lot of the learning strategies also are being designed and analyzed in sort of, my part, if you will, of ECE. So if you've heard about things like reinforcement learning or Q learning, we have a number of colleagues that are working on those kinds of topics. So it's very diverse. I like to think there's something for everyone in ECE, no matter what you're interested in. But I will say a lot of what my people do is kind of applied mathematics, right? So we do a lot of manipulation of mathematical expressions and signals. And it's actually one of the things that I like about ECE is that I get to do math for good.
That's awesome.
Adding to Professor Mitra, like to me, ECEs is super big and broad. I'll give you one example. Let's say we take a cell phone, the iPhone. We actually designed the whole system from scratch. If you think about the electronic engineering component from the hardware side, if you break down a cell phone, there will be chips inside. And inside those chips, there are transistors. So electrical engineers from the device side, they make those tiny transistors, and then they scale up the whole system, make integrated circuits, and then on top, they put the display and also the interaction. So typically, you can break down any electronic systems into components. Let's say for the phone, you have sensors. It can take images. It has an interface, you can touch things, and then the information goes into the computing element, and those computing element processes the sensor data and shows you information through the display. And one electrical engineering, like that engineer can be someone who designs the transistor, can be someone who designs the circuit, can be someone who puts the algorithm inside those integrated circuit chips, and also design the display elements. So it's a super big, broad, and versatile discipline. And usually, like ECE covers all the major areas in electronic systems. Anything to do with electrons, we have an electrical engineer who devises the system.
Yeah, so you also work with novel materials too, right? Like next generation. So like if it might sound crazy, but people are also building like biological chips.
Yeah, so like one example could be like we are thinking about transistors, those made out of silicon, and you can actually use other materials. One example is organic materials. So I do work with organic electronics. So we can use polymer-based transistors, polymer-based sensors. The displays we have on TVs, OLED-based displays, those use novel materials. So these are just examples. You can use existing silicon. Silicon is a very standard. It's been around for over 50 years. But people are looking at new materials, and we have faculties who are experimenting with new materials, how they can use those for making devices and also computing elements.
Sandeep, anything else you want to throw into that?
So I'll build on the two. So electrical engineering, broadly speaking, exists in the intersection of information and the physical world, from my perspective. And the methods that it uses is a lot of, on top of the physics and the information, it also uses a lot of mathematics as Professor Mitra already pointed out, because that's a fundamental way to reason about all of this and put everything together. From an undergraduate point of view, our curriculum is has three different prongs. One prong is basically the physical world, and that has all the materials, devices, and some of the examples of devices that you can relate to are the ones that Professor Khan just shared with us. But a radar is a device. You go to the airport, you see radar, that's a device. Even the phone has a battery, that's a device. You go for an MRI, that's a device. You go for any kind of medical imaging, that's a EE device in variety of ways. So the range of devices we have is basically very broad and encompassing, all encompassing. The second piece is basically the where basically I think so that's one column. One of the prongs of our fork is essentially all the things that go from materials to devices to somehow building systems using those devices, all kinds of useful systems. Second component is basically the world where the system interacts with the whole world through communications over channels and through long distances across planets, and controlling things in robotics, all of those things. The third is basically the heart of computation, which is really helping all of this, all the processing that is needed oftentimes. And that's where I sit, is how do you basically build computational systems? And you can think about computation from point of view of computer science or computer engineering. And the computer science part of it is, how do I think about computation from point of view of what I would like to do, and how can I basically figure out a good way to do it without worrying about all the physical details. People like me say, well, physical details are important, and I can do things efficiently by basically taking into account the physical world. So I am in that slice of computation which says, I understand my computer science colleagues would like to do this. I understand my controls and communication colleagues would like to do this, but I am sitting at that at that interface where I'm saying, now let me see if I can find a way to do this extremely efficient and powerful, building powerful machines that basically run really fast, are and basically consume not that much power, and so on and so forth. So that's where basically we sit. So those are the three prongs of our ECE fork. You will see that in our curriculum. You will get exposure to all of those, and then you will go a little bit deeper on two of those, and then you will basically do your design and other things in one of those. There is something for everyone. If you like physics, this is your home. If you like math,
if you like physics, you want to see what you can do with it, and this is the degree to do with it.
And if you like computation, this is your home. If you like to write code, this is your home. If you want to do machine learning, this is your home. If you want to do chemistry, this is your home. But with an eye to basically making one of these systems and making them efficient.
Well, this is great, Sandeep, and I think I'm going to stay with you for a quick second because you kind of alluded to this, which is, how is the curriculum structured? What can students expect for the undergraduate curriculum? You kind of, as you started going through that, I realized you're describing the curriculum in a broad sense, but what types of classes will they be taking? What types of projects will they be working on? And when does it start? When do they start getting into this?
So, in ECE, we have changed our curriculum in the last 6, 7 years, 8 years. First of all, in ECE, all engineering departments go through an evaluation by an external agency that basically accredits our programs. And one of the interesting points that was made to us when I was the chair of the department and we had this review 5 or 6 or 7 years ago was that it was surprising that how many of our faculty were actually involved in undergraduate education. So I want to basically, start with that, which is not necessarily an answer to Paul's question. It is really that whole cross section of our faculty are engaged in undergraduate education. The second point I want to make is that we start with your electrical engineering education. the reality is that to become an expert, to be able to do something in each one of those fields, in some of the fields of electrical engineering, you require a lot of mathematics before you can actually do real electrical engineering. Professor Mitra talked about that. In some other areas of electrical engineering, you require a lot of physics and mathematics before you can do. Professor Khan talked about that largely. In some areas of electrical engineering, you can start doing engineering right from the beginning, but you just have to build up the mathematics in parallel to be able to do it better in subsequent years. That's a kind of my field. But we have figured out a way to do the mathematics of electrical engineering starting from first semester. Linear algebra, which is really the underpinnings of basically the methods on which all optimization and machine learning methods are based. We teach that in the first semester. Our colleague Antonio Ortega teaches that class. Programming, computational, problem solving, I teach that in the first semester to first year undergraduates. E105, which is Introduction to Electrical Engineering, we basically are revamping that class, and essentially we would have, Dr. Khan or or Dr. Kapadia or both, or some combination.
Yeah, I can add to that. So like we were thinking about how to introduce electrical engineering to students through a guided project approach. So they're gonna see a real world application. So we are thinking about why not design a whole medical device from the scratch, use it, and learn about each of those segments in modules. One of those we were thinking about a optical sensor. So in that one, the students would learn about how these sensors work. And then they will try to build a prototype connecting, let's say, light sources, light sensors. And then once they have the sensing element, they can connect to a readout. So usually like a high school students, they are exposed to Arduino, those type of microcontroller environment. We do programming a lot in electrical engineering. So there's a misconception that we don't do much programming. We extensively use many sorts of programming. In our group, we use Python, C++, MATLAB. So the students do learn programming a lot in the curriculum as well as in the projects. And say once you have the system in place, you can capture the data, and then you can think about how to process the sensor data. So here you'll be working with signal processing. So that's one whole area. So the idea is with that class, we want to introduce from one practical application to show how a whole electronic system works. That's one of the ideas we have for intro to EE 105.
This is the very first class. So I think that's what I think we might have gotten buried a little bit in the conversation, is that the very first class is about the idea of creating that endpoint to then break it down and understand it. So you start to see all of the elements, because as we've discussed so far, just to summarize a lot of what has been said so far, EE is everything. EE is all the time. It's everything everywhere all at once. And so the idea of saying, let's make something that is everything everywhere all at once, and then break it down to understand how signal image processing and hardware architecture and any of the other types of digital logic circuitry comes together. It's a complex beast, but let's understand how it works together. Is that a good summary?
Absolutely.
Yeah, so I just want to
like,
underscore that
yeah.
in the first year, the students will, 50% of the classes the students will take will be electrical engineering classes. And they would be taking those classes with their electrical engineering cohort. So I think there's another side effect of this, a byproduct of this, happy byproduct of this is electrical engineering students get to know each other. And our cohorts are, of reasonable size. So electrical engineering students get an opportunity to basically not only learn a lot about the field starting from their first semester, and but they basically get to form a community of individuals who are interested. So in some sense, because electrical engineering is all so many different things, having that coherence in the community is important for that to basically coalesce with each other. And we basically, the structure essentially that we have in our program essentially allows that. And every year, of course, as you go to upper years, as junior or senior, you will do a lot more courses in any area of engineering. But electrical engineering is unique in our school. In Viterbi School, electrical engineering is unique in that 50% of the classes in the first year are electrical classes, and we'll give you that foundation. The three prongs of the fork, you will get the foundation across all of them, and the classes like that Professor Khan just talked about basically kind of give you a slice of that.
That's great.
Across all those three fronts.
Building community and collaboration is a unique part of our school, and it's great to hear how that's emphasized in the designing of the curriculum. My next question is to talk a little bit about kind of that next phase beyond curriculum, which is a larger part of a university experience, specifically where you all have a lot of experience, which is in research. Can you help us understand what is the research that's going on in the department, or your specific research? We can start with that, and feel free to dive in at whatever level. I mean, Dr. Mitra, would you like to kick it off?
Sure. I think I'm going to use, I was mentioning to my colleagues before we all started that I've been doing some traveling. And so I was in San Jose over the last 2 days, talking about some new work that we've been doing, which was motivated by trying to model really large wireless communication networks, actually really large networks in general, where this amazing PhD student of mine has come up with a strategy to create synthetic data to speed up learning strategies. So this, of course, is a really big issue in AI and machine learning, where one of the challenges is that in some applications, there's just not enough training data available. And I first spoke about this work in a forum where I thought I was going to really stand out like a sore thumb, because it was on industrial AI. So I was surrounded by corporate colleagues, a lot of small startups that are looking to build new AI products for specific industries. At least on the day I was there, I was the only academic speaking. And it turned out that our ideas using actually theories out of Ortega's group, who we've talked about before on graph signal processing, it was creating a lot of interest. And so, and then the next day I went to go visit a company and talked about similar things, but also talked about some new work that we're doing, which really takes advantage of some very precise models for wireless communication channels and uses that model in order to make localization by an eavesdropper really hard. So we've basically designed, again, using mathematics and a lot of linear algebra, spoofing strategies that if you share a very small amount of information, in fact, just 2 numbers, an intended receiver can localize, the transmitter, but nobody else can. And we're also getting a lot of traction on this. So again, mathematical models to describe signals. A lot of what we do, as I said, for these 2 examples, rely on properties of wireless communications and networks, and then designing novel algorithms. We also like to prove properties about these algorithms so that we can make strong statements about how well they work. But these are the 2 topics that we're getting a lot of interest from both our academic colleagues, but also from the corporate world. So it's very exciting.
Other thoughts on research?
So I'll, my research, some of it is technical, and one of the projects that we have right now is on the fact that when these large companies manufacture these chips and sell them to customers, previously it was believed that the chips sold to the customers would basically last the 5 or 7 year lifespan, 3 to 7 year lifespan, with a very low probability of failure in the 100 parts per million to 500 parts per million, which is a fraction of a percentage. But recently, because there are companies like Google and Facebook and Amazon that are running data centers with millions of these chips, they have discovered that they fail actually at 20 times to 100 times far more higher rate than it has been believed for 30 years. So some of my research is to basically understand what is causing these chips to fail at this remarkably larger rate than it has been believed for 30 years. What happened? Where did we mess up, and how can we basically remedy this? So that's a sort of a technical research, but you can see the relevance of that. Anybody should be able to understand that if I buy a chip and if it fails, 20 times more. If my car broke down 20 times more often than it was advertised, I would be really, mad at somebody. And so basically that's sort of a research that we are in ongoing discussions with, a couple of different companies to basically do this kind of work. The second part is essentially, as I said, uh, people believe software is eating the world, but the reality is that the software is slow and expensive in terms of how much power it consumes and things like that. So the question is that if the hardware doesn't, hardware has been improving at its exponential rate, high rate exponential for 50 years. There's nothing in the world that has grown at that rate, but now that is beginning to slow down. And that slowdown actually creates challenges for others, but opportunities for us, electrical engineers. The way it creates challenges for others is that, computer scientists have gone in the direction of abstraction, as I said. So they want to solve the problem without worrying details about how the hardware will actually do some operation. And that is inefficient. And when the system hardware was getting faster and lower power every year and cheaper every year, they didn't care about all the efficiencies. We were worried about those efficiencies, and we would deliver what we could to them, but they were basically not worried because it's cheaper, it's faster, it's lower power. So, yeah, okay, yes. So you have to replace your PC every 3 years, big deal. But now you replace your PC every 3 years, it's not going to get faster. So what do? You build custom design. You build design that is bespoke for a particular application. And for the applications that are used heavily and run for months and years, weeks, days, weeks, and months, you basically want to build special purpose hardware. And so we are building that for a class of mathematical problems in combinatorial optimization called satisfiability, which is the core of an NP complete problem. It's a prototypical NP complete problem. So we are basically building hardware to do that. But turning to undergraduates, it's one of the interesting things about this is that, when I started working on the satisfiability accelerator, a light bulb went into my head. I said, satisfiability is a problem that is simple enough for an undergraduate not only to understand, but to actually contribute to, while it's a lifetime of work to make it faster and efficient. And so I do have actually a bunch of undergraduates in my lab who are essentially working with satisfiability, trying to understand the problem, trying to write code. They're writing their own solvers from scratch. Of course, the first year undergraduate solver doesn't work as well as something that has been optimized by experts for 40, 50 years. But they're able to write their own code to solve satisfiability problems. And then they're able to use their code and the other code that is available as an experimental testbed for new ideas of how they can make satisfiability faster. And they are working mostly on the software layer because even though we are interested in designing hardware, the students need a couple of more years of experience. And once they get those experience, I hope to basically move them into the hardware design aspects of that. So undergraduates are involved in this in a very fundamental way into the problems, which may seem very abstract at first. Satisfiability, what is that? I never heard of satisfiability. Well, but it is a vehicle for a lot of students, and there's a lot of research opportunities. As I mentioned, that I also am the director of the undergraduate honors program across the School of Engineering, and one of the deliverables of that program is that students are required to do a thesis or a commercialization. So I supervise that, and there's a lot of opportunities for that. And that's only one of the many programs in School of Engineering where students get to do research. So there's a Curve program that is run by the Office of Undergraduate this thing, and my students are all supported by Curve. When they place out of Curve, they're supported by provost fellowships for undergraduates, and then they basically do the thesis. So there's a very rich life cycle of, and as I said, honors program is just one of the many programs in School of Engineering for students to continue to do research in the upper years.
Thank you so much.
So I have the dubious distinction of coming up with the acronym CURVE.
Is that your fault? I'll admit to you what I say. I said it's my favorite, my whenever I present on it, I said it's my favorite forced acronym ever.
Yes. Well, we have many talents.
Center for Undergraduate Research in Viterbi Engineering, Curve. I'm like, that took some thinking. So I'm glad to know that
It's a very unique program. So I like from my doctoral and postdoctoral training, I have like interacted with undergraduate students, but it's quite unique to USC that the students can spend 2 semesters in a group focusing on research. And I did see a huge emphasis to encourage first years or second years to join the research groups. I in my first year had almost 10 students. Now I have 12 undergraduate students in my group. So it's it's very I would say like very useful to the students because they get to see research when they start their undergraduate curriculum. For me personally, I got involved in research in my fourth year. So coming to USC and right away getting exposed to research is very valuable for them, and it's been very successful. So uh, I mentioned like the 10 students in my first year, many of them will be co-authors in scientific papers coming out of the group. So like I'll give one example. One of my students, she was looking into how an ingestible can be tracked when it goes through the stomach. And we designed a magnetic coil that creates a magnetic field. And the sensor, like the capsule had a magnetic sensor. So we can essentially backtrack from the sensor data or what's the location of the capsule in the GI tract. And she actually came up with the algorithm. She trained a neural network from the XYZ location. We could basically tell the location of the ingestible. So it's a very unique opportunity compared to other school where students can get exposed to cutting edge. So this is like not an Arduino type of research. So this is cutting edge research right away in their first and second years. So this is super helpful to them.
This is great. I have one last question for you all that I'm going to contribute. But for now, what I wanted to also do is make sure that I announce to the audience that I'm turning on the Q&A feature. So at the bottom of your Zoom window, you can see the Q&A window. Feel free to start loading questions in there, as many as you like, and then start upvoting the ones that you want answered first. So it'll be up to you all as an audience to submit questions and upvote them. And we'll start doing that as I ask this one question. And I'll get back to that Q&A window. So please start jumping in there now with your questions. If you are not able to see that, I think you should be able to. So we should be ready to go. Now, my last question to my panelists. As students are looking at all of the different majors and all the different colleges and universities, one of the things they constantly worry about, as they should, is like, where does this end up leading? And so can you talk about outcomes? Can you talk about where, anecdotally or just, in general, what you got, students that are coming through your program, previous undergrads you know of now, where are they heading? Where are they going? What are they doing? And I know there's a variety of things, both industry and grad programs. Whoever would like to grab this one first.
I'll just briefly note that, a number of the undergraduates I've worked with have gone on to graduate school. In fact, one of the most recent ones is doing a PhD in communications at MIT. And so I'm very biased, but I think the quality of our undergraduates are amazing. And as a result, I'd like to thank both all of you and your talents, but also the programs that we offer you. I think there are just a lot of opportunities. But I'll let others who have more experience talk about this.
So I think our undergraduates, as the field is vast, our undergraduates are placed, very widely. I think about 10% of our undergraduates, or maybe 15%, actually end up getting what is called progressive degree programs. So they basically get a master's degree. It's a progressive degree program is something that you basically sign in your third year, and you essentially get a discount in some sense in terms of number of courses you have to take. You have to take fewer courses than a master's students would have to get a master's here at USC. So a significant percentage of students, by the time they finish, they actually get a master's degree. A percentage of our students, varies a little bit from year to year, basically, but move on to basically, other programs. Some of them in engineering, and some of them in other areas. I know a couple of students who basically have recently taken up a master's program in other universities in finance and other areas. So it's a very broad education that allows you to, you know, mm, our students know enough math and physics to basically kind of, you know, think of careers as quants. You know, not my first choice for electrical engineering students, but it's their life. You know, it's their life, and if that's what they want to do, they are equipped to do that. A lot of our students end up in the communications and you know, controls and robotics, devices, circuits, you know, the whole range of areas. And a good chunk of them actually end up in doctoral programs in leading places. So I have had students who you know, are at a PhD program at Princeton and so on. And so a lot of our students, AEC students, basically end up in doctoral programs across the country in industries as wide-ranging as our discipline is. And a lot of them actually stay and finish the masters quickly, a quick masters before they leave.
So what's fascinating, and thank you for that, is as I opened up the questions, the first question that got the most votes was kind of exactly what I just asked, which is what kind of jobs and internships do undergraduate students in the EC department typically get? And we did essentially cover that, but I think the one thing that we might be missing are companies. And so can we throw out some companies, just start throwing them out that you know that are recruiting the internships and jobs and things off the top of your head?
I know that we have a lot of our graduates that,
Well,
I was going to say SpaceX. Yeah, I think all of the big companies that you would think of, you know, I know companies in the telecom industry, you know, Qualcomm, Ericsson, Nokia. As I said, I was in the Bay Area talking to a number of people. And I should also note that students go both to these large companies, but also there are a lot of interesting smaller organizations and startups that are out there that students also go on to. So
it's a very broad cross section. I mean, our students are, you know, we may think about some of these companies, you know, from my perspective on computer engineering from hardware side, we think about Facebook and Google as software companies, but they are building a lot of hardware. So I see that slice of students basically going to those kind of places with EC background, to those kind of places. You know, in my field, you know, places like Intel and Qualcomm basically employ a lot of design engineers. NVIDIA, Apple are big employers. So, you know, you think about any hardware companies, if you go to materials, etc., you know, etc., etc. I have less direct understanding of the market in that area, but you know, maybe I'm assuming that students basically go to positions in those companies either, also those type of companies. But in computer engineering, I don't know of any company that you would think of as a hardware company where our students don't go. And in even software company, things that you would think of hard software companies have huge growing divisions in hardware, and a lot of our students end up.
Absolutely. There was a question that I think got dismissed because I was asking a follow-up question, so I apologize, but this was to Quyen Vo, and I was trying to decipher her question, but I think I figured it out, so I'm going to rephrase it. Something that is an interesting concept is the computer engineering computer science degree program, which is a joint program administered from ECE and the computer science department. In short, what this is, if you think of computers on a spectrum, there's the software end of the spectrum and the hardware end of the spectrum, and computer engineering, computer science is a combination of those two. While every software degree has a little bit of EE built into it, and every hardware degree has a little bit of programming built into it, this is best thought of as a 50-50 split. And inside of that CECS program, the question was referencing tracks, and essentially that says, do you want to lean in the hardware side, or do you want to lean on the software side? And so that's what that really means, is that that spectrum gets a little bit carried out. As far as an application process is concerned, if you're trying to understand the difference between computer science and electrical computer engineering, which is a lot of the things that we're discussing here today when they talked about software and programming versus hardware, it's really just a question of Yeah, they all go together and they all work together. There's a lot of work that goes on in each of these things. But what, from your instincts coming out of high school, what sounds the most interesting to you? Let's start there. And realizing that if you start in ECE and you want to move to CECS, or if you start in CS, you want to move to CECS, or you're going to move to ECE, that movement happens a lot at USC because the ideas and understanding of what this is all going to be for you is going to be something that's going to happen after you're immersed and after you're inside of the curriculum. So at this point, think of the spectrum and then those details about whether you're going to emphasize or specialize or be in a particular area. That's all down the road that you're not able to answer right now. So don't worry too much about that. So sorry, folks, for taking over that question, but we'll get into the next one. Again, reminder, folks, you went in and upvoted some questions, but you got to keep doing that. Otherwise, they stay stagnant. So please, if you want things to pop to the top, please go ahead and answer those questions. Sophia's asking, does a study abroad experience fit within the engineering program? Yes, it does. I'll answer this question. Overseas programs fit for all of our majors. It's just a question of how and when, and that's something to work on with your advisor because we have a variety of different overseas programs that are integrated into the curriculum, and sometimes not at all. Maybe you want to study abroad over the summer and take Italian courses while you're in Italy, while you're getting a minor in Italian. That's something that can actually happen pretty easily. But the also question is, do you want to actually have an exchange program, which we can do, or you want to do semester or a certain Maymester or fall term? There's lots of different forms of this that students are studying abroad across all of our possible majors. So thank you for that. So I answered that question. Aaron asked the next question, and I'll phrase it to you all. So let's see what you think. What are essential skills and qualities necessary for success in electrical and computer engineering? I think we're all smiling because it's like, yeah, there's very specific skill sets to be successful in electrical computer engineering, different than anything else.
I mean, from the technical side, you need to know your fundamental mathematics and physics. So those are like core to electrical engineering, and then you have to build up on those skills to take up, let's say, the other skill set in terms of linear algebra, or going forward, how to use probability, or like if you're thinking about data science or using like the signal processing aspects of electrical engineering. Many of these core skills go like hand to hand in other disciplines also. So if you're good in math or linear algebra, you'll be using that for doing data science too. So these are used not only just EE, they're used broadly in other disciplines too. So fundamental mathematics and also physics and chemistry. So these are very needed if you're looking at like software or hardware sides.
I'm going to give a non-answer to that. So I think a lot of us think that we choose our disciplines, but I actually think that disciplines choose us because you naturally gravitate towards, areas that you find interesting. A lot of engineers will take very similar classes in their first year, in the sense that, there'll be some physics, chemistry, mathematics, and then you'll explore some of these more specialized topics. We offer a class for all of our first semester students, Freshman Academy, which will expose you to a lot of different disciplines. You'll actually meet students who are different kinds of engineers, and there's always a handful of students who know they want to be an engineer but aren't sure what kind. And so hopefully this will give you a feel. But as I said, I at the risk of dating myself, the wand chooses you.
So I'll give you kind of
that's a Harry Potter reference. That's eternal. That doesn't date you at all.
So I'm going to give you kind of an orthogonal answer because of the vastness of the field. One of the things that is I see important, and it doesn't exist in our curriculum as such, but it exists in the spaces in our curriculum, and I think it's an important thing, is your curiosity and your creativity. I think this is a very fundamental challenge of being any kind of engineer, but definitely electrical engineer because of the diversity of the field. You really need to be able to, put yourself in saying, and I have had students over the 32 years, the students have educated me through their questions. And one of the questions that I get from students, which has educated me a lot, is, you mean I can use what I learned in this other class in your class? And this is a question that comes from a position of innocence, a little bit of fear, because sometimes I'm assuming that students early on have been told, no, we do things differently in this class, but as an engineer, electrical engineer, you really need to be able to connect a lot of dots, and you need to be creative about that process. And being logical, systematic, mathematical, knowing the domain that you're talking about is important. But what is also important is how you navigate that combination to basically find a voice of your own. And I think some of our more successful students are essentially able to do that. But we provide that kind of an opportunity. I don't see research as anything other than providing that opportunity. But we also have other things in our curriculum courses that are designed to do that. We have design courses. We have courses that require you to pull things from multiple courses to basically design something meaningful and something that is personal to you. The thesis that I talked about, or innovation program that I talked about in the part of the honors program, all of this require you to basically kind of put into it something saying, well, why doesn't this exist? Can't we improve this? Well, that requires something that I don't know that much about. So maybe I have to go talk to Professor Mitra. I'm a computer engineering student, but I've never taken her class. But maybe I need to talk to her to figure out, something about that. And then how do I synthesize that in my thought process? I think that is important component of this.
Thank you for that. I want to add one quick thing on this, because sometimes depending on how the question was asked, sometimes it's determining like what skill set do I need now while I'm in high school, and I want to make sure it's math and science preparation, and that's really it. It's not, and there's a lot of concerns that I get a lot through our admission process when they're talking about any engineering major, saying like, hey, electrical and computer engineering sounds really cool, but I don't think I have a lot of electrical and computer engineering experience, and will I be admitted? And I always tell people, like, what high school student has electrical and computer engineering experience? Like, everything they just talked about as far as skill sets are things they're going to teach you, are things that are included in the curriculum, and that's why they're in the curriculum. More often than not these days, in this kind of digital landscape where everybody knows everything at once, people worry about the fact that they don't know something, and that's exactly what this educational process is.
Can I give you, Paul, a simple answer to this question?
Yeah.
If we admit it, you will succeed.
Yeah.
If you admit you will succeed. Don't worry about all that stuff. Just, if we had any doubts about that, we would not admit you. Okay.
Right.
I'm just going to give you a simple answer. You don't need to be afraid of anything. You walk in here and you basically basically just get moving. Okay. If we admit you have what we need. Okay. We will cover the rest. And if you didn't have something small, talk to us. We will find a way to get that to you. Don't worry about this. This is a worry which is basically you should retire right now. If you want to apply with confidence. And if you get admitted, we basically have already given you the seal of approval from our perspective. And if there is a small gap, come and talk to us. We'll find a way to fill it up.
Yeah. And the last thing I would add is, as long as you find what these people talking about interesting, that's the skill set you need. Like, if it sounds cool, then go after it. It's going to be great. All right. Ishan asks the question, what's the ratio for hardware work and software work for the average ECE student?
I can try to.
Yes,
it depends.
So it depends completely on you. So like, if you find hardware is something that you're interested in, you can have like bulk of your coursework and whatever projects you do can be on hardware. From my own experience, so I did my undergrad also in electrical engineering. It was split, like almost like half-half. I didn't know at that time like if I like hardware or software more. In my master's, I extensively worked on computational photonics, and I didn't like that experience that much. And then, like in my PhD, I switched to physical electronics. I like that so much that I'm building my whole career on physical electronics. it's completely up to you what you like. So if you like to do computation software, you can do bulk of your projects and coursework on that. If you like hardware, you're free to move in that direction. Both are fascinating.
Or you can do neither, and you can do math. So,
But
so I think it, as again, we've been saying this, it's a very diverse field. I didn't enjoy my first circuits course, and because I had a parent who was an electrical engineer, they told me to persevere. And then once I took my first signals and systems course, I was hooked. But it's basically applied math, right? So, yes.
so, I would put it slightly differently. I mean, I think not contradictory to what my colleagues have just said, but there is a lot of software. We may think, but we focus on the math. We focus on the models. We focus on Professor Mitra didn't talk about machine learning for dummies. She talked about model-based machine learning. We reason about the world through mathematics, and our systems are, if you are a human system, how human behave, we don't have very good models for that. So then you have machine learning methods that are basically kind of like, don't have that strong root in some basically domain. They basically exist in kind of in some sense pure statistics. But if you are basically building machine learning problems in in communications or controls or in microbial communities, as Professor Mitra talked about, you are rooted in models that things that you actually know a lot about in a very recent way. So the electrical engineering software is very different, and I had to think about this very carefully, because when we created this class that I teach to undergraduates, the first question that rose is, why are we teaching our programming class to our undergraduates? Why don't we just use the computer science course for introduction to programming? And I told our colleagues Kichag and Bhaskar Krishnamachari and Tony Levy, I don't know the answer to this question. Let me teach this for 2 years, and then I'll give you an answer. And my answer is that our students are writing a lot of code. Some may choose not to write a lot of code. That's okay, but a lot of them will write a lot of code. But it's not the volume of code. It is really the mathematics. It's really the combinatorics. It is really the models. Really, code is just a way to express that and to basically kind of process that to solve the problem. So for us, code is just a natural extension of whatever we are doing. My students do a lot of logic, and so their code is essentially a reflection of their thinking about the logic. Professor Mitra students, I'm assuming, think a lot about models and channel
But I was
models.
also going to add, Sandeep, perhaps another difference is that we also tend to use a lot of specialized software packages, right, that are tailored to
Yes.
kinds of problems that we want to solve, and may not be using basic programming, languages as much as we might have done 20, 30 years ago.
And that's because basically the physics of our field or the mathematics of our field is a unique thing, and we're building on that. So there's a library of all the tools and models that are available to us. We're basically building on that. So electrical engineers write code, but they're not known by the lines of code they write. They are known by the deep ideas that that code embodies and the interesting problems that code solves.
Right. I was going to say, I keep talking about how we do applied math, but my graduate students, they all have to write simulations, right, to test and validate the algorithms that we come up with. And, they use a lot of MATLAB, but now because they're doing a lot of comparisons to vanilla neural network algorithms, they're now doing a lot of PyTorch. Mm-hmm. So, and so far, touch wood, our model-based methods outperform a lot of the vanilla AI and machine learning architectures, usually because they require a lot more training data than we do, because we're exploiting the underlying physics of the problems that we're trying to solve. So.
Thank you very much, faculty. And Ishan, thank you for your question. I will add just one short thing to this question, because I think I have another feeling where this is coming from, is a lot of high school students think they're supposed to have their plans figured out before they get here. Like, okay, I better know where I'm going, hardware, software. There's obviously a wall there. And I think hopefully what you understand is that this is a very fluid experience it's very porous. And just from Dr. Khan's experience, this was each stage changed as he went along, and you're going to change. So the idea right now is what sounds cool, take a step into it. You have supportive faculty that will teach, that will guide, that will advise, and your brain will adjust and evolve as you go through this process of what you find fit. And technology in the future, different than technology today too. So things will change as you're changing with it. So don't think you're supposed to have this figured out. Now, we only have time for one more question, and I know that Ubli has indicated interest to answer one of these questions, so we're going to break my rules. And
I kind of hit the wrong button, so
okay.
I can answer it. I've already forgotten which one.
Now, just own it. It's Curve. It says for the Curve program. If we have a particular interest,
absolutely.
Are we allowed to choose groups that fit those?
Absolutely. So what happens is that different faculty post projects, and you essentially get to look at the series of projects and reach out to various faculty. But Curve is not restricted to what's been posted. You can also interact with individual faculty and essentially, have your own project inserted into the Curve framework. So it's very flexible. And honestly, these research relationships work the best when both of you are invested in what you're working on, which is both the faculty member as well as the student. So we have a very flexible program on many axes. Paul talked about this a little bit with respect to curriculum, but it's true for other parts. One of the questions that I think we should try to answer, and I'm not sure that I'm the best one to do it. There have been several questions about double majoring. And people do definitely double major. I know this because the students that I do scholarship interviews with, they all seem to be double majors. When I meet them, and there's some disciplines that show up a lot, like electrical engineering and music. We have a lot of electrical engineering and music double majors, it seems, but I don't think it's quite as common to double major in 2 engineering disciplines, but engineering plus something else is not uncommon. It might take you a little bit longer to finish the degree because you have to fulfill some requirements in both, but it's certainly possible. I don't know, Paul, if you want to take this one on.
Happy to jump in. I will note that when we're doing interviews for scholarships and their high school students, they've got big ideas of what they're going to do, and who knows whether they fulfill on that. So that's a whole other issue. Everybody has, their eyes are bigger than their stomach when it comes to curriculum, is usually what I say. But the ideas of pursuing disparate concepts in your undergraduate education is very common. More often than not, that's a degree in engineering and a minor in something else. I don't know of any students that have, I'm sure they exist, that have double majored in 2 undergraduate engineering programs, because usually it's like you don't get increased value or return on your investment of energy and time to do that. And oftentimes diversity of engineering programs can also exist in your graduate education. So getting an undergraduate degree in one area and moving on to another area in the master's is very common. And that happens in our progressive degree program that was discussed earlier. So what oftentimes the question comes from, that I've found, is that students tend to ask about double majoring across engineering disciplines because they can't choose. Like a lot of our conversation today has been hardware, software, computer science, programming. What is it? Because they're confused about this word computer. I like computers. I know computers. I want to do something there. And they're saying, well, maybe the answer is I'll double major. And that's not the answer. You don't do that. You choose an area to start in and we'll figure it out. And if you're debating between other engineering programs, what's the one that does sound the coolest to you? Let's get started there. And if you don't work out for you, then you switch to the other ones. And that's why the flexibility of our curriculum, that is an ongoing theme of this conversation, flexibility, is the best part of one of our programs here, is that we don't expect you to have it figured out. We're not locking you in. And as you can tell from our faculty today, these are human beings that care about your success. And I think that is a striking difference from a lot of other engineering programs that are out there. These are people that are here to care about you, to teach you, and to get you to the spot where you're going to be successful. And that may or may not be what they do. And so I think that's an important part. I want to end on that, because I like that tone. I like that note. That's a great way to end. And so I would thank you all for attending here today. I really appreciate it. If you missed any part of this, we'll put a recording up on our YouTube page in a little bit. Give us a couple hours at least to get that up. And my largest thanks, please, goes to our faculty for taking time out of their day to chat with you. Dr. Mitra, Dr. Khan, Dr. Gupta, I really appreciate you being here. Thank you so much for sharing your wisdom. And if you all ever need anything from an admission perspective, check out our website for our other events. Always email us if you need anything else. And thank you so much. Have a good night. Bye-bye.
Thank you. Take care.
Yeah, and when you